We were trying to get together, like, to introduce something.
Okay. Good morning, everyone. I want to welcome you to another statistical machine learning class. Of course, today our focus will be on data and addition. Um, in my outline, um, I'm going to walk you through how data is seen as essential ingredient. Talk about data and addition, then how we learn from data. Then I'm also going to walk us through how to distinguish between supervised and unsupervised learning. I will advise that you um, listen and ask question whenever you get stuck. Okay, before uh, I'm going to start today's topic, I quickly want to have a recap on what we did on Friday. Because the assignment I'm actually going to release today, we centered on to explain versus to predict. Um, of course, I said whenever we want to investigate or we want to conduct research, we need to first make our intention known. Do we want to explain or do we want to predict? Of course, well, explanation is about trying to understand relationship between variables. You want to you want to investigate effects of a particular variable on another variable. In your model, you are having an assumption that a particular variable causes the other variable. Okay, so if I'm looking at the effects of smoking habits on the risk of getting a lung disease, then my intention is to explain. But on the other hand, if I don't care about explanation, but what I care about is what is the best prediction for maybe for a particular product. Okay, if I'm only interested in making the best prediction, of course, then it means my goal is not explanatory. Because in the assignment I'm actually going to give today, I'm going to give you some set of research scenarios, and I'm actually going to ask you to identify what intention is. Whether to explain, whether the intention is to explain or to predict. Okay, so you need to indicate that. Okay, back to our topic today. Let me say this. We don't just do what we do. We got a reason why we do what we do. Our intention is actually to uh, to understand our environment. We want to understand our environment. We want to secure our environment. We actually want to provide a practical answers to questions. We ask questions all the time. We need answers to that. And the only way we can get reasonable answers, not just answers, reliable ones, the one that is scientifically based, is actually to seek for knowledge. And of course, uh, what translates into knowledge is the information that you got. And of course, the information that you got, information is readily available I mean, it's available only when you analyze your data with a model. Okay, you confront your data with a model, but you don't just use any our model. You have to be guided. You have to use a model that actually commiserate or with reality, with the data you have. There must be a kind of an agreement between the state of the data and the state of the model. The state of the data and the state of the model must be in agreement before you can actually extract the meaningful information in the data. Because of that, what is very, very essential is data. And that's why you see, I said data, data, and data. I normally tell people around me, if you want to argue with me, come with data. Okay, I'm actually going to give you this definition. Data is an essential ingredient in any research findings. And I'm also going to say that it is one of the most valuable resources that we have in the world. Okay, similar to oil and gas. If you take a look at this economists in 2017, it said data is fuel of the future. Okay, the fuel of the future. And do you know why it said that? Because modern economies, technologies, researchers, government, and so on like that, they actually rely on data. Okay? They rely on data. Okay, now that we understand the significance, the essence of data, then the next is how can we collect data? But the good news is that it's very easy to collect nowadays. With your internet, millions of data are generated every day. If you look, if you with the Facebook, Instagram, TikTok, and so on like that, Snapchat, and so on like that, very easy to collect and generate. Okay, so and you can have it anytime, anywhere. Okay, now after collecting it, now that it's easy to collect, you have the data at your disposal. I also want to say it's also very easy to manipulate and analyze. Okay, no matter the nature of your data set. Okay, with the evolution of software that we have around. Okay, they can be easily manipulated or easily. And that's why I say we have a powerful computing. Okay, the powerful computing help handle bigger and more complex data. And let me tell you this: our ambition will actually translate into more data. We're going to continue to have ambitions. We can never get tired of having ambitions. So, and that's why I say more data, more needs, and ambitions. Our ambition grow when data grows. Okay? Because we actually believe that with data set at hand, then we'll be able to get information that we need. Okay. Now, let me tell you this. Whether in molecular biology or in engineering or in astronomy, I'm actually going to say from agriculture to zoology, from A to Z, okay, the make use of data. A philosopher said, and I quote, when you torture data well enough, the nature will always tell the truth. When you handle your data very well, the nature will tell the truth. We want to speak the mind of a nature, but the only way we can do that is through data. But let me tell you this, you have to be guided, depending on your intention. Then you have to use an appropriate statistical methodology in order for you to get access to reliable the information that we have in the data set. Now, I gave an example here. Molecular biologists gave better understanding of the relationship between gene expression levels and cancer tumors. Let me tell you this. Do you think we begin with you having an understanding? I remember last week I said if you want to have understanding of relationship, then you need to go retrospective, looking backward. And that is synonymous with science, with basic science. The basic science has to do with understanding and explanation. Okay? So, and you know, the moment they understand the relationship that exists between variables, that will lead into what I call new treatment for cancer patients. Okay? And I said here, the astronomers gain new understanding of cosmos from signals collected by improved telescope and communication technologies. You know, every day by day, we have an improvement in technology, and as a result of that, that will lead to new discoveries. I told you from day one, the existence of human, the existence of reality is independent of human knowledge. I'm going to say that again. The existence of physical world is independent of human knowledge. And what we normally try to do is to have some understanding of what is going on around us. And one of the ways to get that understanding is to collect or to have your data. Okay? With data, of course, we will be able to achieve what we have in mind. Okay, so still on data and ambition, engineers make use of data. Okay, not only that, what about bank analysts? Okay, sometimes customers approach bank for loan, and the bank officials acknowledge the fact that we live in a stochastic environment where there's possibility some could default. Okay, they have to use with the data set they have in conjunction with appropriate statistical model, they will be able to figure out the probability of a new customer defaulting on loan. Okay, so if you that was why I said want to make a more accurate prediction of loan performances. Okay, then you need data. Okay, and with that, they'll be able to have more profit because you need to first understand, okay, before you can achieve whatever your intention is. Okay, even in politics, okay, the data become necessary. Okay, if you want to make accurate voting pattern, okay, if a candidate actually wants to improve on winning chance, of course, you need to listen to people, right? By way of, through data. Okay. Now, what about the top companies like Google, Facebook, Amazon, and so on? They make money, by learning about and exploiting our internet browsing pattern. They take advantage. They try to understand what you like, okay, and with that they make more money. Okay, they make more money from that. Okay, so they also taking data. They're taking your data by trying to understand your preference. What you care about. Okay, okay. Now I want to talk about learning from data. We all learn from data. Okay, and let me say this. And that is the reason why American Statistical Association defines statistics as the art and science of learning from data. Okay, We all learn from data. But let me tell you this, if you use inappropriate statistical model or machine learning algorithm, okay, there's possibility you could learn wrongly from data. You could, it can mislead you, okay, depending on whether you are using the right methodology. And that's why you are here. You are here to be guided, okay, statistically, so that at the end of the day, you're going to end up using appropriate algorithm, to learn from your data. We don't want to learn wrongly. Okay, so here I said the amount of data and information collected and stored is constantly increasing due to advances in data collection, computerization of many aspects of life, and breakthrough in storage technology. Because of the fact that we have a highly sophisticated storage device, okay, we do not have any issue with amount of data. And that's why we're going to continue to collect data, okay, new data, okay, and we learn from that, okay. Now, let's take a look at the consequence. Here I said statistical problems have increased both in size and complexity. Let me tell you this. That is expected because the more we get advanced, okay, the more we have data set, the more our ambition is going to increase, the more statistical problem get increased. Because every statistician, okay, or data scientist or researcher that work with data, okay, the moment there's a lot of data in place, data will increase their curiosity of understanding relationship, okay, and with that, statistical problem increase by the day. We got some old problems, okay. We're also going to have some new problem as well. So that is not surprising, and that's why we call that a consequence, okay. Now, somebody said the statistician or data analyst job makes sense of all this data. Let me tell you this. When you take a look at data, data are just figures, mere figures, but they have a lot of hidden information. Okay, we don't just look at them as mere figures, but as statistician, as data scientists, we make sense of those figures. And how we make sense of those figures requires that we should be statistically inclined. And that's why you are here. Okay, there's a lot to do with data. We may want to identify pattern, we may want to identify trend, we may want to see whether there's an upward movement or downward movement or something remains stagnant. But particularly when you are working with time series data, data you collected over time. Or you may want to uncover interesting relationship that exists, okay? Or you want to predict the future observation. So there's a lot that we can actually learn from data. Okay, and let me tell you this because the data that we have are massive in nature, okay? If you look into the complexity of this data set, that is not going to be an issue because of the fact that we are advancing in technology. We have a faster computer and so on like that. And let me also tell you this. When I have data set, okay, because of the our computing skills or the graphical skills, we can actually have effective graphical representation of our data. Because at times we want to draw picture. We don't just draw picture. We want to draw picture that actually tell a story. Okay, we got a lot of pictures that we draw in statistics. Okay, you got about box plot, you got about pie chart, you are a biohistogram and so on like that. Of course, all of that fall under a graphical representation of data set. Okay, so we have a new graphic capabilities. Technology helps. Okay, technology actually play a very huge role. Okay, in analysis of data. Okay, okay. I'll still on learning from data. I said, but not always. Faster computers do not solve all problems. And I said some problems are inherently computationally intractable. Okay, you need to know this fact because as time goes on, we may be working with algorithm that may take longer, that may take forever to converge, particularly when we are working on numerical analysis or where maybe we need to have a very good initial starting point before the algorithm can converge, stuff like that. Okay, we're just trying to tell you that having faster computer does not solve all problem all the time. We still need to do something, okay, to make sure the algorithm work. So as time goes on in this class, we're going to talk about a topic that we call converse theory. Okay, in optimization, what can actually guarantee global minimum in terms of when we are into optimization. Okay, we're gonna let you know. Okay, as time goes on. Okay, easy. And I said something here. Easy black box data analysis can lead to a lot of misuse and misunderstanding. I'm going to say this. Machine learning algorithms are black box. Okay? When you look at, we may not be able to know what is in the black box, but the experience shows that the result from that, the black box in machine learning algorithm has a very huge predictive power, but it lack explanatory power. Statistical model has a very huge explanatory power because of what? Because of transparency. There's no black box. When it comes to statistical model, okay, when you have a statistical model, you can actually see for yourself how estimation of parameter is done, how our confidence interval is being undertaken. We can see transparency in that. But the issue with statistical model, they do not have a very huge predictive power. But the issue with a black box in machine learning algorithm, they have a high predictive power, but they lack explanatory power. And that is the reason why in this course we are considering statistical machine learning principle where we're going to have opportunity to gain or to benefit from statistical rigor and machine and flexibility of machine learning algorithm. Okay, so I said the blackboard data analysis could lead to misuse and misunderstanding, which I just wanted to know that. Now, let me tell you this. Machine learning algorithms are more flexible, but they could overfit. What do I mean by overfitness? I need you to pay attention. If you don't understand, ask me a question. Okay, when I say it could overfit, let me tell you this. I want to go historical now. I want to give you this story. I said on Friday, the worst enemy of everyone in scientific community is bias. Okay, the worst enemy. Okay, I think I'm going to use this. The worst enemy of everyone in scientific community is bias. Okay, what is bias? Bias arises as a result of model misspecification. Let me tell you this, when you are seeking an explanatory goal, whether as a statistician or physicist or chemist or biologist or psychologist or criminology and so on like that, we normally start with module specification. Okay, we specify our module in advance. We specified our module according to our thought. Okay, and when we specify this module, it's actually going to come with assumptions. Okay, okay. Now, when our module is incorrectly specified, then you have induced bias. Okay, and what people in scientific community are trying to do is to minimize, is to reduce bias. And you know what they normally do to reduce bias? They add more variables to the model. When you add so many variables to the model, even though you are going to succeed in reducing bias, but you will create another problem that I call high variance. High variance, you're going to create another problem that I call high variance. High variance lead to overfitting. Okay, what do I mean by high variance? It means your model will be more sensitive to subset of training data. Okay, your model is going to be more sensitive to subset of training data. Your model is going to perform great on the training data, but perform poorly on the test data. I'm going to say that again. A model overfit, when I talk about overfitness, it means your model will perform a great job on the training data, but your model will perform poorly on the test data. Don't forget, when you want to work with model, what you normally do with your algorithm, you normally partition your data set into two sets. You're going to have, some data set for training or the other one for testing. Okay, your model, if there's a problem of overfitness, your model is going to perform great on the training data, but going to perform poorly on the unseen data. Unseen data is the test data. So in that situation, your model is overfitting. Your model is not good for generalization. Okay, we just wanted to know that. So even though we want flexibility, but when a model is more flexible, then that model will overfit. Okay. Is there any question moving forward? Is there any question moving forward? You all understand that, right? Okay. Now let's come to this. I said understanding underlying assumptions and interpreting or inferential finding correctly remain as important as ever. I'm going to say this again. Statisticians, a majority in the scientific community, when they are seeking explanatory goal, when they are seeking causal goal, they normally start with the model specification in advance. Okay, they start with the model specification in advance, even before seeing data, even before collecting data. Okay, they already have their underlying theory, they have their model, and when they specify their model, okay, model specification come with assumptions. Module specification come with assumptions. Let me tell you this. Assumptions are limitation of a model. Okay? What make a model to be fantastic, what make a model to do a great job is when assumptions underline the use of the model met. If the assumptions are not met, then you cannot trust your model. And that is the reason why you need to be aware of this. Okay? So understanding underlying assumptions in a model is very, very crucial. Does that make sense? Okay? So a model is good as assumptions put into a model. I'm going to say that again. A model is good as assumption put into a model. If assumptions are not met, you cannot trust your model. Okay, we just want you to understand that. But let me tell you this. When you are seeking explanatory goal, when you are using statistical models, okay, we normally want to ensure that assumptions are met. But when you are into when you go into using machine learning algorithm, okay, the assumptions can be relaxed. Okay, assumption can be relaxed. Okay, they do not have a stringent assumptions when it comes to applying machine learning algorithm. But let me tell you this: statistical machine learning is not a replacement for statistics. Statistical machine learning is not a replacement for machine learning algorithm. Okay, if you take a look at chief economist works in Google, he said, I keep saying the sexy job in the next 10 years will be statisticians. Okay, the ability to take data, okay, to be able to understand it, to process it, to extract value from it, to visualize it, and to communicate it. Okay, so what I'm doing right now, I'm communicating that, because communication is also a key. Okay, because when statistical ideas are not well communicated, that could lead to misuse of statistics. Okay, okay. So he said that is going to be a hugely important skill in the next decades. Can you see that? Not only at the professional level, but even at educational levels. I'm actually going to say across different field, of course. This actually true. Okay. I want us to go into the class proper. Okay, what is machine learning? Of course, I said we have these are kind of techniques, that we design to figure out information from data. Okay, we want to learn from data. Okay, the algorithm that we actually use to learn from data. Okay, and this is the way the data is going to look like before you can apply machine learning algorithm. Okay, you need to have multivariate data set. When I say multivariate data set, it means you have so many features. You have more than one measurement at a time. Maybe you got some variables. I remember in this class I talk about crime variables, like I talk about assault, burglary, property theft, something like that. Or you want to talk about clinical variables that are more than one. Okay, and that is what so I'm actually going to use matrix. Okay, because the idea of matrix algebra is actually going to be used here because I get so many variables. So x is equal to x1, x2 up to xp. So here I'm trying to say I got p numbers of features, p numbers of variables. Okay, and let me tell you this: these variables, they could be quantitative. They can also be categorical. When I say categorical, they have more than one level. Okay, maybe I'm talking about race, I'm talking about class of income and stuff like that. And they can also be mixed. There's possibility when you collect your data, you could collect your data can be as a mixture of categorical and a quantitative variables. We're just trying to let you know about it. So that is why it's called multivariate data. Okay, and it's an extension of univariate. Univariate data is only when I'm focusing on one variable at a time, one measurement at a time. Maybe I'm focusing on weight or I'm focusing on height. And bivariate is when I have two measurements at a time. But multivariate is when I have more than two variables. Okay, now let me tell you this. When you have variables, okay, a situation where response variable is among them, the response variable is the outcome variable, then the approach of machine learning you're going to use is different from when there is no label. In this course, 4051, we're going to focus more on unsupervised learning. Unsupervised learning is when we actually there's no label, there's no response variable. All variables that we have, they are explanatory variables. Does that make sense? But in 4052, okay, in 4052, the focus will be more on supervised learning. But in this course, 4051, our focus will be on on supervised learning. Okay? So but I just wanted to know uh in the uh in the supervised learning, we may actually where there's a label, where there's a response variable, you may want to be able to you want to investigate relationship between X and Y. S actually represent the explanatory variables and Y is the response variable. Or you may want to predict Y from S. When you are doing all of that, you are expected to use supervised learning techniques. So generally speaking, there are two types of learning techniques, the supervised learning and unsupervised learning, which is what I'm trying to show you here. Okay, let me tell you this. We got to go using supervised learning techniques. We got to go using unsupervised learning techniques. We don't just do what we do. We got a reason why we do what we do. And that will be driven by our intention. Situation where you observe both X and Y, the X is a set of explanatory variables, Y is response variable, then you're actually going to use supervised learning. And in supervised learning, you want to investigate connection between variable. You want to have the understanding of how S causes Y. You also want to make a prediction of Y from S. The technique that you're going to use is supervised learning. Okay, an example of such that that you've done before, your regression analysis, your analysis of covariance, your analysis of variance, and so on like that, they are all classified under supervised learning. Okay, now let's talk about unsupervised. And I said in this class, our focus will be on unsupervised learning where we only observe X, we do not observe Y. We do not have access to label. We do not have access to the outcome variable. Now, if we do not, let me tell you this. At times, what actually drive our intention may actually be the nature of the data that we have. If I have my data set and I realize there's no label, there's no response variable, there's no outcome variable, I only have a set of explanatory variable, then my goal is going to be change. My goal is going to be either to summarize or understand or visualize relationship, or maybe what I actually want to do is just to partition observations into different groups, or using based on certain characteristics. Okay, so the goal in supervised learning is different from the goal in unsupervised learning. And of course, in this class, since our focus is going to be on supervised learning, I'm going to, some topics like principal component analysis is unsupervised. The, factor analysis, the graph, and so on, clustering, and so on like that, they are unsupervised. Okay, so we're going to we're going to focus more on them. Okay. Now, these are the topics that we're going to focus on. All these topics actually fall under unsupervised learning. What do I mean by unsupervised learning? Once again, in our data set, we do not have response variable Y. We only have set of independent variable S. Okay, now depending on what we're looking for, if we actually want to group, Like for instance, if I happen to be a physician in a clinic and I want to group my patients into different groups, I want to put them in different groups. I want to have a penalized medicine, not a medicine for all. Then I'm actually going to use a clustering approach. Okay, clustering has to do with a partitioning of observations into different groups, just based on certain characteristics. So in this class, I'm going to walk you through different type of clustering algorithm, k-means, k-medoid, hierarchical clustering, and so on like that. Okay, then we're also going to talk about dimensionality reduction technique like principal component analysis. All of that, they fall under unsupervised learning, the factor analysis, the matrix completion, matrix factorization, the graphical model, the test data, and graph data mining. Okay, so let me tell you this. What we're doing right now, statistical machine learning, okay, because of the fact that there is statistical, okay, in the title, okay, the knowledge of probability and statistics will provide us a mathematical framework. I remember on Wednesday when we started this class, I said statistical machine learning actually fall at the point of intersection, okay, intersection between the probability, statistics, and programming, okay. The probability, why do we need probability? That will enable us to know how data are generated. Why do we need statistics? That will enable us to learn how we learn from data, okay, and how we actually conduct inference, okay. And of course, we also need the knowledge of linear algebra. The linear algebra will enable us to know how model computes, okay. So I just wanted to see that. Okay, I want to go into example now. I actually want to talk about, I want to use example on US city crime data. Okay, these are crime variables. Okay, now in these crime variables, because there's no response variable, there's no outcome variable. Okay, if I want to analyze this data set, depending on my intention, I'm actually going to use technique from unsupervised learning. Okay, now, and that's why I say goal is to summarize and visualize. The goal is not about how a variable causes the other variable. The goal is not about making a prediction here because this is actually unsupervised learning. Okay, so I have series. The series here, they're actually going to serve as the observations, okay? The crime variables, those are the variables, okay? Now, if I have a data set of this nature, okay? And if I want to have a sense of this data set, I will first, I will go graphical first, okay? I want to go graphical. Take a look at this. I'm going graphical now, okay? I want you to see something here. This is what we call a scatter plot matrix with a density plot imposed. Okay, now what is my intention here? Okay, I actually want to see relationship between crime variables. From what I've seen here, I can see violent crimes, variables are positively related. Okay, the property crime variables are also positively related, and I can see there's a weak relationship between a violent crime variables and property crime variables. But if you take a look at what you see in the diagonal, what you see in the diagonal here represent a density plot. What do we use density plot to do? The density plot will actually tell us the distribution, okay? The distribution in the variable, okay? In a particular variable, okay? Murder, in rape, in robbery, and so on like that. This is actually showing us it is skewed to the right. That is showing a positive skewness. The positive skewness actually means we normally have few cities. Few cities used to have large numbers of violent crime, while majority of the city has very they have no violent crime. Okay, we don't just draw picture. All this picture actually telling stories. Okay, now if you take a look at this guy, okay, we have a lot of cities here, okay, and we actually want to reduce all of this to two dimension. Okay, we're going to talk about this in principal component analysis, where we artificially create dimensions. Okay, instead of her having a lot of variables, can we have a way to use just two variables? If you take a look at what I have inside here, these are cities, okay? These are cities. When cities are far away, okay? When you take a look at city like Atlanta, Miami, and St. Louis, okay, you're actually talking about maybe more violent city, okay? When they are far away, when they are when they are far to the left, okay, then that would be that they are less violent. Further to the right, more violent. Further to the left, less violent. Okay, these are actually telling story. We're still going to talk about all of this. I'm just showing you. Take a look at this. We have an optical character recognition. Okay, this is handwriting. How can we actually predict alphabet in this image? It's not clear. Okay, now if you take a look at that, we have a data set, okay, which actually is images of single handwriting, and each image, okay, each image has dimension. I think we know that. Each image has 20 by 16 pixels. When I multiply 20 by 16, what does that mean? I got 320. Then it means the number of explanatory variables is 320. I have x1, x2, s3 up to s320. But what is my response variable, the outcome? The outcome variable is A to Z and 0 to 9. How many alphabet do we have in English? 26, right? How many figures? 10. 10 plus 26. And that is the reason why we have 36 levels of Y. If I want to analyze this, I'm actually going to use a supervised learning because my response variable is observed. Okay, I'm actually moving. Okay, so like I said, you'll be able to predict that. Now, this is another one that we call it map. Okay, if I actually want to know, if I have so many variables and I want to know the relationship between them, we can draw it map. Okay, so take a look at that. Each particular color represents a particular relationship. Okay, then we can also do clustering. I'm going to walk you through how we cluster, how we partition variables into different groups. You can read more on that. That's a correlation. We have a distance matrix representation. Okay, there's something that we call MDS, multidimensional scaling. How we can project observation in high dimensional into a lower dimensional space, and we'll be able to preserve the original distance among variables. We're going to make use of MDS, so we're still going to talk about this. Okay, and let me also tell you this: in matrix completion, we're also going to learn that approach in this class, particularly for recommender system. Okay, here they ask some people to rate movies. Of course, the movies that I don't watch, I'm not going to rate that. That's why you see some missing values. How do we now impute values that are missing? We're actually going to walk you through that technique in this class that we call matrix completion. Okay? Then we're also going to talk about community collaborations. Take a look at this. How researchers work together, how they co-authored, and so on like that. So you can read more on this. But lastly, before I go, according to George Boss, all models are wrong, but some are useful. But let me tell you this: if we specify a model and we can verify assumptions, we can make our model to be safe and be useful. That's all what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.